Good day, everyone. I am Agnes Altea Daan, and I'm with Kristen Jovan Llamas, and we are going to report these topics. So, first is the principles of the gyroscope. Second is the gyrocompass and the repeater system. Third is the errors of the gyrocompass and their corrections. So, these are the two principles of a gyroscope: the gyroscopic inertia and the gyroscopic precession. Gyroscopic inertia, or rigidity in space, is the inherent tendency of a rotating body to maintain its plane of rotation, illustrated by the example of a hoop rolling in a straight line when set in motion resisting tipping. Rooted in Newton's first law of motion, emphasizing the continuity of rotational direction unless acted upon by external forces. So, gyroscopic inertia, often referred to as rigidity in space, encapsulates the intrinsic tendency of a rotating body to steadfastly preserve its plane of rotation. This phenomenon manifests vividly in gyroscopes, where a spinning wheel, once set in motion, resists tilting or deviating from its original orientation. The underlying principle finds its roots in Sir Isaac Newton's first law of motion, asserting that the rotating object persists in its state of motion unless compelled otherwise by external forces. In the context of a gyroscope, this translates to the spinning wheel's commitment to maintaining the direction of its rotational plane, showcasing a remarkable resistance to any external attempts to alter its orientation. Imagine a spinning gyroscope on board a vessel. Its gyroscopic inertia ensures stability, allowing to resist the vessel's rolling, pitching, yawing, and thus providing a reliable and unwavering indication of direction. For the gyroscopic precession is the gyro's response to external forces, causing it to turn about an axis perpendicular to the applied force. It is demonstrated by applying force to the gyro, resulting in precession about a vertical axis. Precession is a gyro's attempt to maintain its rotational state, aligning with Newton's laws and resisting changes imposed by external influences. So, complementary to the gyroscopic inertia, precession is the gyro's response to external forces, demonstrating a distinctive turning or precessing about an axis perpendicular to the applied force. When force is exerted on the gyroscope, whether about its horizontal or vertical axis, it reacts by precessing around the axis orthogonal to the applied force. So this behavior is a consequence of the gyro's determination to preserve its rotational state despite external influences, aligning with the fundamental principles articulated by the Newton's laws. The dynamic interplay between gyroscopic inertia and precession forms the basis for the stable and predictable behaviors for gyroscopes in various applications, from toys like spinning tops to sophisticated navigation systems like gyrocompasses. Understanding the principles of gyroscopic inertia and precession is fundamental to understanding the stable and predictable behavior of gyroscopes. Inertia ensures the gyro maintains its rotational plane, resisting external forces, while precession showcases the gyro's dynamic response to applied forces, underlying the harmony with Newton's laws of motion. These principles form the foundation for various practical applications, from toys to advanced navigation systems.
Characteristics of a typical compass. Apparent rotation, an effect that can occur when the compass is subjected to external forces or accelerations, leading to an apparent movement of the compass card or display that may not correspond to the actual change in the vessel's heading. This phenomenon is a result of the gyrocompass system's sensitivity to accelerations and disturbances. The Earth turns in the direction of the arrow, or clockwise with an angular velocity of 1 revolution every 24 hours, carrying the gyro around with it. But the gyro, because of its inertia, maintains its original plane of rotation in regards to space, just as it did when its base was tilted as shown in the picture. With respect to the Earth, however, the gyro rotates about its horizontal axis with an equal velocity, but in the opposite direction to the rotation of the Earth. After 3 hours, the end of the axle, which was pointing east, apparently is elevated at an angle of 45 degrees. After 6 hours, 90 degrees. After 12 hours, 180 degrees, and so on, until at the end of 24 hours, it is back where it started. The reader will perceive that the difference between the gyroscopic inertia and apparent rotation is simply one of point of view. As far as space is concerned, the gyro remains fixed. In comparison with the Earth, however, the gyro actually rotates as described above. It 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 is this rotation which makes it possible to apply force of gravity so as to convert the gyroscope into a north-seeking gyrocompass. Damping factor. The extent of the damping action is governed by the displacement of the mercury ballistics connecting link from the center line. Commercial compasses are given a damping factor of 66%. The the eccentricity of the connecting link is such that each swing of the gyro axle from the meridian is one-third of the preceding swing. The amplitude is being reduced by 66% at each oscillation. If the compass is started 30 degrees east of the meridian, the first swing will carry the compass to 10 degrees west, the return swing to 3 to 1/3 degrees east, then 1 to 1/9 degrees west, and so on, until it comes to rest. The picture shows graphically the damping characteristics of the gyrocompass. Period of oscillation. The natural period of the compass, the time it takes to perform a complete oscillation from A to B in the picture, is 85 minutes. The period of oscillation is governed by two factors. First is the angular momentum of the gyro, which is the product of weight, speed, and square of radius of gyration. And second is the torque about the horizontal axis supplied by the action of the mercury ballistics. This in return is governed by the free surface of the mercury in the containers and the distance of the containers from horizontal axis. If the weight or the speed of the gyro is increased, the period of oscillation will be longer. If the free surface of the mercury is increased, the period of oscillation will be shorter. The compass is designed with this long period so as to function satisfactorily on a moving ship at sea. A compass with much longer or much shorter period would have an incorrect ballistic deflection and would show some deviation when turning. Compensating weights. Unsymmetrical distribution of weight is another potential source of disturbance when the compass is swinging, which must be neutralized. When the asymmetrical weight shown in the picture is swung in the plane A to B, centrifugal stresses act upon it in such a way as to cause all of its particles to place themselves as far away as possible from the axis of swing. This causes tendency to turn as indicated by the arrows. The same effect may be observed when a watch is swung back and forth on its chain through a small arc. In the gyrocompass, this effect is avoided by the use of compensating weights, which permits of a symmetrical distribution of weight about the vertical axis. Latitude correction. The latitude correction is necessary because of the eccentric connection employed to damp the oscillation of the compass. The correction is made by means of a latitude adjustment scale, no special knowledge of the problem being required in order to make the correction. At the equator, where only the horizontal components of the Earth's rotation affects the gyro, The axle of the compass is horizontal and parallel to the Earth's axis. At the, at the equator, therefore, as soon as the compass has settled in the meridian, the ballistic will be at rest and the compass may be considered as a true gyroscope. If we move the compass to a point to the north or south of the equator, however, it will be affected by the vertical as well as the horizontal component of the Earth's rotation. At the point of north of the equator, for instance, the north end of the gyro axle tends to turn toward the east and rise as the Earth rotates out from beneath it, as shown in the picture. It is apparent that the true north end of the gyro axle must be precessed continuously in a westerly direction toward the meridian as fast as it is being displaced by the vertical component of the Earth's rotation. The force necessary to do this is obtained automatically by the simultaneous heat tilt of the mercury ballistics, which permits an accumulation of mercury in the lower or south containers so as to precess the axle continuously toward the meridian. Ship speed and course. The relatively show angular movement of the Earth's rotation provides the motive force for the north-seeking precessional movement of the compass. When a vessel is traveling over the Earth's surface, however, and therefore about the Earth's center, the vessel's movement is compounded with that of the Earth. If the direction of the travel is east or west, the vessel's motion only adds to or subtract from the Earth's motion, and the effect on the indication of the compass is negligible. In picture case 1, the line AB represents the movement of a vessel steaming due north for a given period of time. Line A and C represents the movement of the Earth in the same period of time. The actual path taken by the vessel relative to the Earth's rotation is A and D. And A and C is the normal plane of rotation. A and D is the actual plane of rotation due to combined movement of Earth and ship. As far as the gyrocompass is concerned, therefore, a new meridian E and F is produced, which is at right angles to the line A and D. At higher latitudes, the movement of the Earth is relatively smaller. The new apparent meridian is displaced farther from the actual meridian and a larger correction is required. Thus, the amount of the correction is dependent upon the latitude of the ship, which is the case 2. The displacement of the gyro axle is to the west for the northerly courses and to the east for southerly courses, and the angular difference between the actual meridian and this new apparent meridian depends upon, first, the ship's speed, second, the ship's course, as it is only the northerly or southerly components of the course which are to be taken into account, and the third, the latitude, as the higher the latitude, the smaller the Earth's surface speed, and therefore the greater the effect of the ship's speed. Transmission of the gyrocompass heading to the repeaters. First is the master compass. Discovers and maintains the true north heading reading with the help of gyroscope. Includes the north-seeking element, its housing, and a follow-up mechanism. The primary gyrocompass system installed on a ship. The gyrocompass is a critical navigation instrument that determines the vessel's true heading by utilizing the principles of gyroscopic motion and aligning itself with the Earth's rotation axis. The main gyrocompass is often designated as the master compass because it serves as the central and authoritative source of heading information. This primary gyrocompass provides accurate and reliable data essential for navigation, course plotting, and steering. The master compass is designed to automatically seek true north, ensuring that it remains aligned with the Earth's rotation for precise heading reference. Its gyroscopic rigidity allows it to resist external forces and remain stable even in dynamic sea conditions. In larger vessels or those with high navigational demands, redundancy measures may be implemented with multiple gyro compass systems where one is designated as the master and others act as a backup. This redundancy enhances the reliability of heading information, crucial for the safety and efficiency of maritime navigation. The master compass heading information is often integrated into broader navigation system of the vessel, contributing to a comprehensive and coordinated approach to navigation. Control panel governs the electrical operation of the system and ascertains the running condition by means of suitable meter used for controlling the operation of the master compass and for indicating condition of operating such as current and voltage value. The control panel of a compass on ship serves as the operational hub for managing and monitoring the gyrocompass system. This user interface, typically located on the ship's bridge, provides navigators with essential tools for controlling the gyrocompass and ensuring accurate heading information. The control panel features a range of functionalities, including a prominent heading display that shows the real-time vessel heading derived from the gyrocompass. Operators can make manual adjustments and calibrations using control knobs and buttons, ensuring the system's accuracy and responsiveness. The control panel also includes indicators and alarms to promptly alert users to any anomalies or errors in the gyrocompass system. It allows for the selection of different operating modes such as standby or follow-up modes to cater to varying navigational requirements. Additionally, the control panel facilitates the initiation of calibration procedures critical for maintaining the precision of the gyrocompass. Operators may interact with the control panel to monitor the power status of the gyrocompass system and receive information about the overall health of the system. The interface of the often integrates with other navigation instrument and system on the vessel. Advanced feature may include data output interfaces for data lodging, integration with networks, or transmission to repeater compasses located in different parts of the ship. Overall, the control panel is a crucial component, providing navigators with a centralized means of managing the gyrocompass system for safe and effective maritime navigation. Repeater panel, mounted directly below the control panel, carries switches for controlling the repeater compasses. The repeater panel of a compass on ship serves as a secondary display unit strategically located in different areas of the vessel to provide real-time heading information. Connected to the main gyrocompass system, the repeater panel acts as a remote indicator, allowing multiple users across the ship to access accurate heading data without direct reference to the main compass unit. Typically equipped with a compass card or digital readout, the repeater panel displays the vessel's true heading, contributing to enhanced situational awareness among navigational personnel. The gimbal system within the repeater compass enables it to remain stable despite the ship's motion, ensuring that the displayed heading remains accurate and reliable. The repeater panel plays a crucial role in disseminating essential navigation data, especially in scenarios where direct visibility of the main compass may be limited. This redundancy in heading display contributes to the safety and efficiency of maritime operations, allowing various individuals or teams to monitor the vessel's heading in different locations. Additionally, the repeaters panel may incorporate features such as dimming controls and alarms to optimize visibility and alert navigators to any anomalies or deviation in the heading information. Overall, the repeater panel serves as a key component in the integrated navigation system of a ship, facilitating accurate and accessible heading data across various points on the vessel. follow-up panel, mounted directly below the repeater panel, carries the vacuum tube that drives the follow-up mechanism of the master compass. The gyrocompass employs that A to C amplifier type of follow-up control. The amplifier panel used is external to the compass and is described in detail in a separate pamphlet entitled Amplifier Panel. For convenience, the operation will be described briefly here. A follow-up transformer is mounted on a phantom element so as to be normally aligned with an armature carried by the sensitive element. The transformer has three legs. The center leg is energized from one phase of the 210 cycle supply to the gyro motor, while the two other outer legs are connected to the vacuum tube amplifier in such a way that when the transformer and armature are aligned, there is no signal to the amplifier. When the sensitive element moves away from the phantom element, the signal to the amplifier corresponds in direction and amount to the direction and amount of such movement. The amplifier augments the input signals so as to control two rectifier tubes which energizes the azimuth motor armature. Since the field of this motor is continuously excited from the D to C supply, the motor drives the phantom element so as to bring the transformer again opposite the armature on the sensitive element. Then the input to the amplifier ceases and the motor stops. Motor generator set converts the ship's supply to a three-phase variable frequency supply for driving the gyros. It is crucial component within the gyrocompass system designed to provide the necessary power for the gyroscopes and associated equipment. Operating on the principle of converting electrical energy into mechanical energy and vice versa, the motor generator ensures the continuous rotation of the gyroscope, maintaining its gyroscopic rigidity and stability. In this system, the motor aspect drives the gyrocompass system during periods of acceleration or changes in the ship course, while the generator aspects converts the kinetic energy of the spinning gyroscope back into electrical energy to sustain its motion. This dynamic process is integral to the accuracy and functionality of the gyrocompass, ensuring that it remains aligned with the Earth's rotation and provides reliable heading information for navigation. The motor generation unit is a key element in the power supply chain of the gyrocompass, contributing to the overall precision and effectiveness of the navigation system on maritime vessel. Course recorder makes a continuous record of the maneuvering on a moving strip of paper. The importance of the course recorder can hardly be overestimated. In everyday use, it provides a visual check upon the quality of the steering, giving a permanent record of every angular movement of the ship's head at the time such movement takes place. Properly annotated, the course recorder chart supplements the ship's log, and the owner, who cannot afford to gamble with fog, reefs, and shows, is afforded a further safeguard as his valuable property moves from one place to another in pursuit of profitable cargoes. Many times the course recorder has been deciding factor in collision cases and has saved the owners thousands of dollars in costly litigation. When automatic steering through the gyropilot is employed, the course recorder shows graphically when the best steering is obtained, and by this means the weather and rudder adjustment on the gyropilot can be set to secure the most accurate result for any set condition. The course recorder is a complete unit operating on the repeater circuit from the master compass. It comprises a repeater motor which drives the controlling mechanism for an indicator dial and a pair of ink pens. A clock control drive roller feeds a paper chart under the pens at the proper rate, and a spring driven rewind roller winds up the paper and keeps it taut. The action of the rewind roller is similar to that of any ordinary window shade, except that an automatic lock is provided on the spring drive to guard against excessive speed. Alarm unit indicates failure of the ship's supply. Since the compass equipment is dependent on the ship's supply, and its accuracy may be seriously affected by a failure or an interruption of the current, it is essential that adequate warning be given in case the supply does fail, so, so that steps may be taken to remedy the difficulty at once. For this reason, an alarm unit arranged to sound an alarm in the wheelhouse in case the 70-volt DC supply is interrupted is supplied with the equipment. The alarm unit compromises a weatherproof case containing a voltage relay, a buzzer, a set of dry cells which supply current for operating the buzzer, and a toggle switch mounted on the front of the case. The relay is connected across the 70-volt repeater supply, preferably at the bridge. When the compass supply is normal, the relay armature is held in place by the energized magnet coil. The circuit to the buzzer is controlled by the toggle switch, which ordinarily is turned so as to silence the repeater compasses, indicates failure of the ship's supply. The repeater compass consists of a small DC step-by-step motor mounted in a casing. A lamp for illuminating the repeater card is mounted under the repeater motor. The repeater bottom cover may be removed for access to the lamp. A dimmer switch for controlling the brilliancy of the repeater will be found in the repeater stand.
The next topics are starting, settling, and adjusting a gyrocompass from shut-off condition. Second, procedures for the correct reading of ship's heading or course shown on the gyrocompass. And lastly, switching on and aligning gyro repeaters with a master gyro. Preparation to start. First, preparations should be begun preferably at least 4 hours before the compass is required for service. Second, make certain that all supply switches are open. Third, unlock binacle top cover, open one door, and make sure that vertical ring and rotor case locks are applied. Fourth, take hold of both sides of phantom and vertical rings and turn them slowly until compass card indicates approximate heading of ship. The compass should never be turned in azimuth with the power off by pressure on compensator weights or mercury ballistic. Next. Next is check the height of oil on oil well windows. Make sure that the oil level is just even with center of dot on window and that oil levels is the same on both sides of the compass. Next is to test alarm by throwing switch on alarm unit for a second or so to make sure relay functions. Next is to adjust speed and latitude and auxiliary latitude correctors to proper setting. Next. Starting compass. First is to throw control switch on control panel to on. Second, pull out circuit breaker plunger on control panel to energize motor generator. Hold hold plunger out by hand until motor generator speeds up in about 5 seconds. Third, when starting alongside the dock, wait until rotor is up to speed or in approximately 10 minutes. Then turn on the follow-up switch on amplifier panel or when starting up at sea, release the rotor case and vertical ring locking latches immediately and steady the rotor case by hand until rotor is up to speed. Fourth, wait 1 minute for rectifier tube filaments to heat up. Next is to release rotor case and vertical ring locking latches. Next, turn on azimuth motor switch at amplifier panel. Synchronize all repeaters to the same heading as the master compass and then close all the repeater switches. Next, turn switch at alarm unit so as to silence alarm. And then reset compass on ship's heading by pressing down on one or the other of the rotor case, bearing housing, and if necessary, level the rotor by pressing against the vertical ring until bubble is on normal settled position. Check repeaters and synchronize if necessary. Setting compass on meridian when direction of north is known. After compass is up to speed and operating normally, precess compass by pressing on top of either rotor case bearing housing until zero on compass card points true north, at which time the card will indicate the true heading of the ship. Then level the case by bringing bubble to normal settled position and allow compass 1 hour to settle.
Setting compass on meridian when direction of north is unknown. When within 2 hours after rotor has come up to speed, level the case approximately 21 minutes later, level it again. Approximately 21 minutes later, level it a third time. The compass then will indicate approximately the true meridian. When the bubble remains at its normal operating position, the compass has settled on the true meridian. Within 1 hour after rotor has come up to speed, level the case and observe rate of travel of rotor case level bubble in minutes of arc for any convenient period of time. Divide number of minutes of arc through which bubble traveled by number of minutes of time allowed for the test. Multiply this quotient by the constant 5. Within 1 hour after rotor has come up to speed, if bubble moves to south at rate of 6 minutes of arc in 2 minutes of time, when compass heading was 125 degrees, then north end of compass is pointing approximately 6.5 times 5 equals 15 degrees west of the meridian, and it should be precessed this number of degrees to the east, or to 125 degrees minus 15 degrees is equals to 110 degrees. Level the case again, observe bubble movement, and make a finer correction if and when necessary. Within 1 hour after rotor has come up to speed, care should be taken that compass is not started exactly 180 degrees off the meridian, as bubble will travel very slowly when compass is heading in such a direction. The settling position of the gyro axle relative to the meridian is reached when the bubble finally occupies its normal settled position in the level. Setting the speed and latitude corrector. When compass is in operation, the corrector should be set for the approximate speed and latitude of the ship. These settings need to be not to be changed for small variation in speed and latitude, but should be kept within 3 knots and 3 degrees respectively. Setting the speed and latitude corrector. To set corrector, turn knob 57 until the scale line corresponding to the ship's latitude on the movable latitude bar intersects the curve representing the ship's speed on the speed plate across which the latitude bar is movable. Setting the auxiliary latitude corrector. To set the auxiliary corrector, turn knob 54 until line engraved on lubber ring coincides with approximate local latitude mark on adjustable block of correction. Gyrocompass alarms. If alarm sounds during normal compass operation, a momentary failure of the supply current will cause buzzer to sound until the supply is restored, and in such case the accuracy of the compass will not be affected. It is advisable, however, to check repeaters with master compass after any momentary failure of the supply. If alarm continues to sound, the current failure evidently is more than temporary. Turn switch off to silence buzzer. Examine control panel immediately. The circuit breaker is adjusted to open approximately 5 seconds after the ship's supply fails. If on examination the breaker is found open, repeat instructions for starting compass at sea. Check master compass and repeaters. Stopping compass. First is open repeater switches, then turn alarm switch to silence buzzer, turn off azimuth motor switch, then turn off follow-up switch, then turn toggle switch on control panel to off, then followed by if stopping compass at sea during heavy weather when considerable motion is imparted to the compass, steady rotor by hand until it stops, then lock it with locking latches. If stopping at dock, there is no need of supporting rotor by hand. It may be locked immediately. Inspect the equipment and clean same if convenient. The equipment can best be cleaned while it is still warm. Under normal operation, the rotor case is uncomfortably hot to the bare hand. This should occasion no alarm as the normal operating temperature is approximately 45 degrees Celsius higher than room temperature. Keep oil level even with center of dot in oil well windows at each end of rotor case. Keep binocle doors closed and cover locked whenever the compass is left unattended. Allow no unauthorized person to tamper with it any time. With ships having 220-volt DC supply, the operating instructions are somewhat different from the preceding. Refer to separate instruction pamphlet provided with 220-volt control panel. Shipboard routine maintenance for gyrocompass and repeater system. Each watch. Routine inspection each watch. Check repeaters with master compass to be sure repeater system is functioning properly. If supply fails for any reasons, be sure to check and if necessary synchronize repeaters as soon as supply is restored. Check compass by azimuth observation if possible. The speed and latitude corrector and auxiliary latitude corrector should be properly reset whenever changes of speed and latitude make resetting necessary. Inspect compass to guard against any abnormal condition of operation. Each week. Check alarm unit by turning switch on alarm unit and noting the buzzer sounds. Then check all electrical connection to make sure they are tight, clean, and free from oil. Then lastly, clean and oil parts as indicated on charts. Each month. Polish the glass over the repeater card. Clean the repeater stand if it is in an exposed position. Check a line of azimuth motor brushes. Clean and oil parts as indicated on charts. Cleaning chart at monthly intervals. Clean inside of binacle and all mechanical compass parts with a soft cloth moistened in carbon tetrachloride. Wipe dry after cleaning. Check all electrical connections to make sure they are tight, clean, and free from oil. Cleaning chart. Master compass. Corrector cosine cam must be cleaned monthly. Collector rings must be cleaned monthly. Azimuth motor commutator and brushes must be cleaned monthly. Transmitter must be cleaned monthly, and rotor bearing, housing, and oil window must be cleaned every 3 months. And lastly, commutator and brushes must be cleaned monthly. Oiling chart. General. Weekly oilings may be omitted where such application would disturb the compass. However, it is recommended that the interval between such oilings be not greater than 2 weeks. Oiling chart. General. Corrector. Corrector must be oiled monthly. Transmitter weekly. Corrector cosine cam monthly. Ballistic link bearing weekly. 12 fathom steam bearings and upper vertical ring guide bearing weekly. Rotor bearings at weekly intervals. Azimuth weekly. Ballistic bearings weekly. Gimbal rings monthly. Motor generator every 3 months. IMO performance standards for a gyrocompass. Accuracy and stability, settling time, resistance to external forces, response time, temperature and environmental conditions, alarm systems, integration with navigation systems, power supply, requirements, calibration and maintenance, follow-up system, manual controls.
The last topic is the errors of the gyrocompass and their corrections. Next. The first is latitude or damping errors and the actions to correct them. Error. This is a constant error in which the magnitude is directly proportional to the Earth's rotation at any given time. This error is corrected internally by offsetting the lubber's line or with a small movable weight attached to the casting. Latitude or damping errors in a gyrocompass are persistent inaccuracies directly related to the Earth's rotation at a specific latitude. As a gyrocompass operates, it encounters challenges at the higher latitudes due to the inverse relationships between course speed and the cosine of latitude. This relationship becomes infinite at the poles, rendering the gyrocompass less effective. Additionally, damping errors are directly proportional to the tangent of latitude, exacerbating inaccuracies at higher altitudes. So to address these challenges, an internal correction mechanism is employed. This involves offsetting the lubber's line, which is a reference line on the compass. Alternatively, a small movable weight can be strategically attached to the casting. So these adjustments serve to counteract the latitude or damping errors, ensuring that the gyrocompass remains reliable and accurate across various latitudinal conditions. By internally compensating for the Earth's rotation and latitude-related factors, these corrective measures enhance the gyrocompass's performance and reliability during navigation and different geographic locations. Second is the course and speed errors and the actions to correct them. Error is this is caused by the fact that a gyrocompass only moves directly east or west when it is stationary or placed on a vessel moving exactly east or west. Correction. These errors can be corrected internally by means of a cosine cam mounted on the underside of the azimuth gear, which removes most of the error. Course and speed errors in the gyrocompass stem from the limitation that the compass primarily moves directly east or west when either stationary or on a vessel traveling exactly in those cardinal directions. The magnitude of the speed error is further influenced by the ship's speed, course, and latitude. This means that the gyrocompass may introduce inaccuracies when the vessel deviates from an east or west course. To rectify these errors, an internal correction mechanism is employed. Specifically, a cosine cam is strategically mounted on the underside of the azimuth gear within the gyrocompass. This cam plays a pivotal role in mitigating the course and speed errors by dynamically adjusting the compass readings based on the vessel's course, speed, and latitude. By incorporating this corrective measure, the gyrocompass can effectively compensate for deviations from an east or west course, thereby enhancing its accuracy and reliability in a variety of navigational scenarios. The utilization of the cosine cam represents a sophisticated internal solution that ensures the gyrocompass remains a dependable tool for navigation on vessels with diverse courses and speeds. Next. Next is tilt errors and the actions to correct it. Tilt errors occur during vessel rolling or pitching, leading to inaccurate gyrocompass readings. Correction: gyrocompasses are equipped with leveling mechanisms to mitigate tilt errors. These mechanisms dynamically adjust the orientation of gyrocompass, counteracting the effects of vessel motion and maintaining accuracy. Tilt errors in gyrocompass arise when a vessel experiences rolling or pitching motions, causing inaccuracies in the compass readings. So these errors can be particularly problematic during periods of rough seas or turbulent conditions. To address this challenge, gyrocompasses are equipped with advanced leveling mechanisms designed to counteract tilt errors. These mechanisms dynamically adjust the orientation of the gyrocompass in real time, aligning it with the stable horizon regardless of the vessel's motion. By actively compensating for rolling or pitching of the ship, these leveling mechanisms ensure that the gyro compass maintains accuracy, providing reliable navigation information to the crew. This feature is crucial for maritime operations as it follows the gyro compass to deliver consistent and precise readings in challenging sea conditions, contributing to the overall safety and efficiency of navigation on the open waters. Lastly is the errors caused by acceleration of the compass. Error changes in ship speed can result in temporary errors as the gyro compass adapts to acceleration or deceleration. Correction: implementing an acceleration or deceleration correction system is a key. This system ensures prompt adjustments in the gyro compass to variation in ship speed, minimizing errors during changes in acceleration. So, errors induced by changes in ship speed, known as acceleration errors, can introduce temporary inaccuracies as the gyro compass adapts to alterations in acceleration or deceleration. These errors are particularly notable during shifts in the vessel's speed, impacting gyro compass's ability to provide precise navigation data. So to rectify this, a crucial correction system comes into play: the acceleration or deceleration correction system. This system is designed to make swift and automatic adjustments within the gyro compass, ensuring it remains synchronized and the varying speed of the ship. By promptly compensating for changes in acceleration, this correction system minimizes errors and guarantees that the gyro compass maintains accuracy, offering reliable information for navigation purposes. This feature is integral to the overall effectiveness of the gyrocompass in dynamic maritime environments where Vessels frequently experience changes in speed during their operations.